Hello friends, welcome back to this lecture series in aerodynamics. Today we will be continuing with the terms, very important terms in aerodynamics called as angular velocity and vorticity. So what is this angular velocity? All of you might know the linear velocity. That is, if I ask you at what velocity or at what speed are you riding the bike, you may say, sir, I am riding at 60 km per hour. So that is the speed, that is your linear speed, right? So what is the difference between speed and velocity? Whenever you describe velocity, you will give it a direction. So that is velocity. Now what is the difference between linear velocity and angular velocity? Angular velocity is the angle straight every second, whereas linear velocity is the linear distance covered every second. So to understand the angular velocity of a fluid element, consider a small fluid element. If you want to define its angular velocity and in turn you want to define what is vorticity for that particular fluid flow, then we have to understand how the fluid element behaves or what physical transformation it goes into when we do the analysis, right? So in order to understand, let's consider an element A, B and C. So these three elements, let's say at time t, so that is the first position, and distance between A and B is represented by dy, and u is the velocity vector in x direction and v is the velocity vector in y direction. So similarly for at point C, the velocity vector in y direction changes to v plus dou v by dou x into dx. So v is the velocity vector in y direction plus the change in velocity in with distance x. So that is dou v by dou x multiplied by dx, the total distance between A and C point. Similarly, the velocity vector in x direction at point B is the velocity vector u plus dou u by dou y, that is the rate of change of velocity in x direction multiplied by the distance dy. Now at this point I would like to clarify what is the difference between dou y and dy. Dou y is the rate at which, let's say, if I can take dou y as 1, dou y as 2. If I take it as 1, what is the change in velocity, that is u, per unit change in y? So that is dou y. And dy is the distance, actual distance between A and B, right? So that is basically the difference between dou and d. So at this point, we have defined the velocities at all the 3 points A, B and C, and also we have defined the distance between these 3 points. Let's say at t plus del t, after del t time, the fluid element moves to a newer position where position of point A is fixed, point B and point C position gets changed. Now by how much? What is the change? The C has been displaced by a value del theta 2 and B, the point B has been displaced by the magnitude of del theta 1, but since this is in the clockwise direction, so it is negative. So we have defined a fluid element at time t and we have defined the same fluid element at time t plus del t, right? So with these two conditions, we will try to analyze the angular velocity of this particular fluid element. Now let's try to define the angular velocity of the fluid element in terms of derivatives of the velocity field. What do you mean by derivatives of the velocity field? I want to express the net angular velocity in terms of derivatives of linear velocities, right? Let's assume that u, v and w are the linear velocities in x, y and z direction respectively. Similarly, omega x, omega y and omega z are the angular velocities in x, y and z direction. So if I want to write the net angular velocity in terms of angular velocities in respective direction, so that would be this equation: omega is equal to omega x into I plus omega y into j plus omega z into k. In the vectorial form, I have described the net angular velocity. Now if I convert all the omega x, omega y and omega z into the respective linear velocities, so I get omega x as 1 by 2 into dou omega by dou w by dou y minus dou v by dou z, where w and v are the velocity vectors in z and y directions respectively. Right? So what this term tells, dou w by dou y, tells is what is the change in linear velocity, that is w, with change in y direction, right? With change in y in z direction. So dou w by dou y represents the change in linear velocity w with respect to the change in z direction minus dou v by dou z. Now the difference of this gives the angular velocity in x direction. So in x direction, how much angle the fluid element has been sweeping, that is given by half dou w by dou y minus dou v by dou z. Similarly, the angular velocity in y direction is given as dou u by dou z minus dou w by dou x into j. So this is angular velocity in y direction, of course, divided by 2. Similarly, the angular velocity in z direction is given by 1 by 2 into dou v by dou x minus dou u by dou y. So this is the angular velocity in x direction, y direction and z direction. Now the vectorial sum of these three angular velocities gives the net angular velocity of the fluid element, right? So let's call this as equation number 1. Now if I try to represent this element in space and time domain, I am going to get, I will define the axis system, that is x, y and z axis, and this is the elemental fluid element, and its velocity, that is the linear velocity, you can see it is following a streamline, right? So it is in a streamline, but at that instant, what is its angular velocity? That is represented by omega. So that is the difference between linear velocity and angular velocity. How much angle the fluid element is sweeping every second, that is angular velocity. How much distance the fluid element is covering, that is linear velocity. So I hope you understood the difference between angular velocity and linear velocity. Now the question is, why we have to define angular velocity at first place? Linear velocity is not enough? Now the answer is, fluid element can go in any direction within the fluid. So that is the reason, unlike solid, we cannot define linear velocities for a fluid element. It can go in any direction. So it can be linear sometimes, or it can be angular, or sometimes it may be combination of both, linear as well as angular. So it is very important to define angular velocity, which in turn I can define it in some of linear velocities. Let's continue with the discussion. Now once you understood what the angular velocity is, now we will see why we have defined angular velocity. Let's define a term called as vorticity. It tells the spinning motion of a continuum near any point. So this is vorticity. So in order to define vorticity, I will take the help of angular velocity. Now what is the relationship between angular velocity and vorticity if we see? So vorticity, I represent it by a Greek term called as zeta, which is equal to 2 times the angular velocity. If I substitute the value of omega in this particular equation, I get zeta as equation number 2. So only thing is 2 and 2 will get cancelled. All the differential of velocity vector remains. So this is vorticity. Let's call this as equation number 2. Now let's define vorticity in another form. So vorticity is nothing but the curl of a velocity. We have already discussed what is a gradient, what is a divergence, and what is the curl of a vector, right? So in this case, curl of velocity represents the vorticity. So that let's call that as equation number 3. So this particular definition leads to two important observations. First observation is, if the curl of a velocity vector is not equal to 0, then that flow is called as rotational flow. Right? We will see what is a rotational flow. It implies that the fluid element has a finite angular velocity. Means, what is the opposite of rotational? Irrotational. Means the fluid elements are not rotating, right? They are not sweeping any angle, right? So this particular flow is called as rotational flow. That is the case when the curl of a vector, velocity vector, is not equal to 0, which means curl of a velocity exists. If the curl of a velocity is a finite value, then that kind of flow is called as rotational flow. Now, second case obviously is when the curl of a velocity vector is 0. So if it is 0, the flow is irrotational flow, which means the vorticity is 0. Whenever vorticity is 0, the flow will be irrotational, which means the fluid element doesn't sweep any angle, or angular velocity is 0. Let's try to understand what is the difference between rotational and irrotational flow. As you can see in this particular diagram, there are two streamlines. The top streamline, the fluid element is rotating at each and every point. Same case in the lower streamline, but here the fluid element is rotating about y-axis. Now here in the second streamline, the fluid element is revolving about x-axis. But in both the cases, the fluid element is rotational. Now if you compare this with the irrotational flow, as you can see, the one streamline on the top, the fluid elements are moving at the same rate without changing its attitude. There is no change in angle. So when there is no change in angle, their angular velocity will be 0 with respect to time, of course. But if you see the below streamline, this particular streamline, the fluid element is of course changing its shape, right? Which means the fluid elements particles nearby are sweeping some angle. But if you see the immediately next element after time, let's say t plus 2, the change in angle is again reverted back, and it reverts back in such a way that it will not only sweep back to its original position, it will try to overcome the change by moving in the opposite direction. So as you can see, the angle change in compared to first element at, let's say, time t is equal to 0 to time t is equal to 1, the change in angle is del theta and minus del theta. Now the same two elements, if you can see, after like t plus 2 and t plus 3, at t plus 3 it sweeps back. Like once it sweeps to minus theta, at t plus 2 it comes back to its original position. But because there was a change initially, it should overcome this particular change by going in the opposite direction. Now this is what another fluid element is also doing. So it is going in the opposite direction just to overcome the change. So both minus theta and plus theta will get cancelled up, and hence giving irrotational flow. Let's try to understand the condition for irrotationality, right? Whenever I say the flow is rotational or irrotational, what condition defines those situations of the flow. So we are going to try and get a mathematical form which will define whether a flow is rotational or irrotational, right? So this is important to our discussion in aerodynamics. If I recall the equation for vorticity, I get this equation number 2, that is dou omega by dou y minus dou v by dou z into I plus dou u by dou z minus dou w by dou x into j plus dou v by dou x minus dou u by dou y into k. So this we already designated it as equation number 2. Now if the flow is two-dimensional in xy plane, right, which means the fluid element is allowed to move only in x and y directions. So what happens to the net vorticity then? So both the angular velocity, the vorticity in x direction and the vorticity in y direction will become 0, and only the vorticity in z direction remains. So that is, the net vorticity for a two-dimensional flow case is nothing but dou v by dou x, that is the change in velocity v with respect to change in x direction, and the change in velocity vector u with respect to change in y, right? So this is the vorticity equation for a two-dimensional flow. Now for irrotational flow, as we have seen in the previous discussion, the curl of a velocity vector is 0, or in other words, vorticity is 0, right? Equating this equation to 0, I get dou v by dou x minus dou u by dou y as 0. Let's call this as equation number 4. So this condition is the condition for irrotationality for 2D flows, right? For this particular discussion, we will limit it to 2D flows. 3D is bit complicated because you are including the fluid molecule even in z direction. So that is bit complicated for this particular course. Now once we define the condition for irrotationality, what is the need to distinguish between rotational and irrotational flow? Usually in engineering sciences, the methodology we follow is, first we will try to get an equation for an ideal case. If you take, for example, the first law of thermodynamics, second law, third law. First law simply tells that work and heat transfers can be interchanged. It doesn't tell which side is possible, how much is possible, and that is told by second law. That is how we are going to build the scientific concepts. First we will define an ideal case of fluid flow. Of course, in this case it is irrotational flow, and at the first glance it appears that irrotational flow is impractical. It is not possible. All real flows are rotational, right? Not necessarily. Most of the real flows can be approximated for irrotational flow. Isn't it interesting? Now the question is why? That is what we are going to see in this particular section. Why we have to distinguish rotational with irrotational flow? Or can I assume all the flows as irrotational, or do I have to assume all the flows as rotational and do complex calculations for simple problem? The first point, why we should understand the difference between rotational and irrotational, and why we have to identify these two flows. So in the first reason is, the irrotational flows are easy to analyze than rotational flows. That is because the angular velocity will be 0 or the net vorticity will be 0. So if that is the case for a two-dimensional flow, just now we saw the equation, it includes just two differential terms. So that is why irrotational flows are easy to analyze than the rotational flows. Next we have Most of the aerodynamic problems can be approximated as irrotational. This, as we discussed earlier, almost all aerodynamic problems at low velocity, of course, and before the wake region can be approximated as irrotational flow. In other words, if I assume the flow to be rotational and do the calculations, compare it with assuming it as irrotational flow and doing all the calculations, the difference in the values will be negligible. So that is the reason why most of the aerodynamic applications we assume the flow to be irrotational. Now the best example in aerospace where it would be rotational and irrotational is when the flow is smoothly flowing over the airfoil surface, the flow will be irrotational because there is no undue pressure distribution and the flow sticks to the surface and moves only in x and y direction. But if I increase the angle of attack, the flow starts to detach from the surface towards the leading edge. Now there forms the trailing edge vertices or the wake region where you can see the flow to be rotational, where vertices actually exist or the vorticity actually exists, and it is no more an irrotational flow. The flow becomes rotational once the flow detaches from the surface. Now we have spent enough time in understanding what do you mean by flow separation in previous lectures. Another reason why we have to distinguish between rotational and irrotational flow is rotational flow exists only in the thin viscous boundary layers. So in other words, in a flow, very thin boundary layer exists. Within that boundary layer, the flow will be irrotational. Within that boundary layer, the flow will be rotational. Beyond that, the flow becomes irrotational. Means we can easily assume that the practical aerodynamic case most of the times will be irrotational. Again, outside the boundary layer, the flow is frequently irrotational. So this avoids the complex calculation involved in the rotational flow analysis. Right? So once the moment I assume the flow to be irrotational, the equations become simpler because we equate the vorticity to be 0 and the differential forms of linear velocities only will be remained in the equation. Before moving on to the next concept, let's solve a simple problem and try to understand what vorticity is. So I'm taking the same previous example where the velocity field is given by velocity vectors, that is u is equal to y by x square plus y square and v is equal to minus x by x square plus y square. So for this particular flow field, we have to calculate the vorticity. I want you to pause the video and try to get the solution of this problem. First of all, try to understand what is asked. Recall all the equations what we have derived in the previous discussion and try to apply those equations to this particular velocity field and try to get the value of vorticity. Take your time, pause this video and come back. I hope you got the answer. Now the procedure is very simple. We have already discussed what is a curl of a vector quantity. So in this case, that vector quantity is velocity. So the vorticity is nothing but curl of velocity vector. So that I can write it in the form of a determinant in which the first row consists of I, j and k. The second row consists of the del terms dou by dou x, dou by dou y and dou by dou z. And the third row consists of the velocity vectors in x, y and z direction, u, v and w respectively. I have a differential, I have the velocity vector field which are the functions of x and y. So that I am going to substitute in this particular determinant. First I, j, k the directions and the differential del terms
and substituting these values, the value of u as y by x square plus y square, the value of v as minus x by x square plus y square, and w as 0. If you solve this determinant, we are going to get I multiply it with the determinant of the second and third row and second and third column. So that would be dou by dou y into 0, that is of course 0, and dou by dou z of minus x divided by x square plus y square. There is no term to differentiate with respect to z, hence this differential, that is I into 0 minus 0. So I multiplied by 0 minus 0 minus the j vector. So I will neglect the first row and second column. Then I have dou by dou x, that is the differentiation with respect to x of 0 is of course 0. Next I have the differentiation of y by x square plus y square with respect to z. And since the equation doesn't consist the z term, it is a constant. So the differentiation of a constant with respect to z again is 0. That is this second term. Then moving on to k plus k, I neglect the first row and the third column. Now I get some meaningful terms, that is the differentiation of minus x divided by x square plus y square with respect to x minus the differentiation of y by x square plus y square with respect to y, that is the second term. So if I simplify, I get the value of vorticity as 0. Kindly recall, whenever the value of vorticity is 0, that means the flow is irrotational. Right? So that is a conclusion we can get from this particular example, that is the given velocity flow field, that is u and v, the flow is irrotational except at the origin where x square plus y square is equal to 0, that is the equation of a circle. Except at center, at all other points the flow is irrotational. So that is the conclusion of this particular problem. Hope you have understood this. I want you to practice more problems on vorticity, giving various functions of velocity vectors. Try it and tell me in the comment section below.